Good evening and welcome to PyData Manchester. Thanks for joining us for the June edition of our lockdown specials, I suppose. As always, get in contact with us at PyDataMCR on Twitter, join the Slack, or for more long-term things, we've got the podcast too. I'm John Carney, one of the volunteers and organisers. Joe is behind the scenes setting up the streaming and recording and stuff that makes it work. And Jennifer and Sean can both be found in the YouTube chat, the Slack conversation, and on Twitter. If you've got any issues at all, make sure to contact one of us. If you go to the PyData Manchester Twitter page, you can find links to all of us. So anything around anything at all around feedback or code of conduct issues, let us know. And speaking of the code of conduct, PyData Manchester is a professional meetup event, so it should be treated like a professional event. It's important that it's inclusive, harassment-free. Even while we're online, all these values still apply. So if there's anything you feel comfortable with, then let us know. So upcoming events, we've got PyData UK tomorrow. While PyData Manchester helped do the May event, feels like a huge amount of time ago. It's Cambridge and Lancaster, I believe, organising the event tomorrow. So sounds like they got some really good speakers. So make sure you check that out. We've got our code night on the Wednesday, the 1st of July, which I guess is a week on Wednesday, very soon. Her Plus Data is on the July the 9th, and PyData Northwest, as always, the 3rd Thursday of July. I say as always, I'm just assuming it's the 3rd Thursday of July. We've got podcasts as well. As I mentioned earlier, Recommendation Systems, Hera Hussein from May, and Adam Fletcher from Equal Experts. His podcast will be coming out on Thursday. So if you got if you have a job you're looking to hire for, if you're looking to get hired for a job, if you organize a meetup or any events, pop into the Slack. We've got the jobs channel, we've got a Manchester channel, I think there's a London channel. Wherever it's relevant, pop your announcement in there. If you want to get involved, whether it be a speaker or as a podcast guest, sponsor, or getting involved with the code of conduct enforcement and stuff like that, just let us know. We're on Twitter. You can contact us via Meetup. Not so much after the event, although we'll certainly be in the Slack chat. Let us know. So this evening, we've got Tim Hargreaves, who is a data scientist at AstraZeneca. I believe while he does his year in industry from the university. Tim is going to be talking about neuroevolution. It sounds frankly fascinating, and I hope I can keep up, but I'm really excited for this one. If you've got any questions at all, pop them in the Slido using the event code 40559. We'll make sure that's in the Slack as well, just in case anyone's looking for it. We want to thank our sponsors, Horsefly Analytics and Cathcart Associates, as well as non-convex, who help with all of PyData on the PyData stack. So thank you to all of those. Without you all, we wouldn't be able to do this. Afterwards, make sure to join us in the Slack and get involved in the conversation, both during and afterwards. After Tim's talk, we can pass on any questions to him. So without further ado, I'll pass it over to you, Tim.
Okay, thank you, John. I'll share my screen.
Yeah.
Okay, great. So thank you, everyone, for attending this talk, When Biology Meets Data Science, an Introduction to Neuroevolution. So I'll start with a few introductions, specifically a bit of background about myself. So as mentioned, my name is Tim, and I'm an undergraduate mathematics and statistics student at the University of Warwick. I'm currently taking a year out to do a placement year at AstraZeneca, the pharmaceutical company, and that is as a data scientist. And generally, my interests lie in computational statistics and machine learning. So anything involving prediction or probability, that's my sort of thing. And so there are three parts to this talk. The first is introducing this notion of evolutionary algorithms, and that is algorithms that try and use the notions of evolutionary biology to try and solve complicated optimization problems. We'll then have a quick recap of neural networks, very high level, just introducing the key ideas. And then we'll move on to a project that I worked on in applying the ideas of evolutionary algorithms to try and design and optimize neural networks. And so I want to try and keep this talk very high level. We won't get into too much of the technical details or the code, but at the end, I'll link to further reading as well as the source code and presentation material if you want to have a look at that after. And then we'll end with some questions, and I'll try my best to answer those. So let's start with the motivation for this talk. It all started a few months back when I was working on a project and trying to design a neural network. And I'd done an okay job, but I wanted to push it much further and really get as much accuracy as I possibly could. And I had a look at the available methods for trying to improve your model's performance and try to optimize it. And frankly, it just didn't quite go far enough that I didn't feel like I could really pull out all the performance I wanted. So let's start with a rundown of the common methods for trying to improve the structure or parameters of a neural network. And so the first solution might be just to copy someone else's neural network. That if you're working on a project that is similar to something done either on Medium or in literature, then you might be able to take someone else's work, take their neural network and apply it to your problem. Now, this can work sometimes, but it requires an element of trust that the solution you're copying was implemented correctly and in an optimal way. It also might not be the case that when you take this model for another data set and try and apply it to your own similar data set, that things will generalize perfectly. And you might lose some performance in doing that. So another approach might be just to use your intuition, to try and use all the experience you've built in using neural networks to have a good guess at what the best structures and parameters should be. Now, the problem with this is that it's lacking in reproducibility. It's very subjective. And even if you work your way through trial and error to a solution that works, it might be hard to then write down exactly your thought process to getting there. And it also requires you to have that intuition. It can take a long time to develop that, and you might be mistaken in your initial beliefs. So then we get onto some more of the computational methods. We could use a brute force or a random search. That would involve considering all the possible combinations of model structures and parameters and just trying them and seeing what works. And for small models and for small search spaces, this is completely valid. But as this grows, it typically will grow exponentially, and it will soon become intractable for any computer to do. And because projects have deadlines and electricity costs money, we can't be leaving our computer to run these forever. We then move on to these gradient-based methods, and these revolve around imagining the space we're optimizing over as a sort of surface, and we're trying to move down that surface, like with gravity, to minimize it. And this has flaws in that if that surface is not convex, it's not a clear valley shape with a clear minimum, then we could easily end up getting in a local minimum that is good, but not as good as it could be if we searched over the whole of the landscape. We also run into these issues with the high parameters and structure of our neural network not having a natural sense of derivative, of gradient. If we don't have that, then it can be difficult to figure out how to do gradient descent, or we have to approximate these gradients, and that can be computationally expensive. And finally, we have these Bayesian methods, and these are kind of a fairly new thing gaining more popularity. I know that IBM are doing a lot of work on their Bayesian optimizers for neural networks. But the problem is that they're quite confusing, that you have to understand this notion of a surrogate model. You need to decide what your priors, that is, a way of encoding your initial beliefs statistically. And even then, if you can nail those things down, it can be hard to know how well your solution is converging. And so really, this is a long way of saying that designing and optimizing the structure of a neural network is a hard problem. And yet, evolution, biology, managed to make its own neural network just fine. And so this got me thinking, well, if evolution could do this, maybe we could use a similar sort of approach to design the structures and tune the hyperparameters of neural networks. And that project is what this talk is all about. So we'll start with an introduction to this notion of evolutionary algorithms, just a high-level overview of how and why they work, with an example at the end. And so I'll start with a quick recap of how evolution behaves. And I'm not a biologist, this will not be completely accurate, but I hope it gives a general idea of the underlying process. And so we start with this idea of an organism or individual, and these are the smallest units of a population. And we can differentiate them by their genetic code. That's kind of the information that describes them. And that genetic code will then express itself in the physical attributes of the organism. And now different attributes will impact the likelihood of an organism surviving. And survival will often lead to reproduction. And when an organism reproduces, it's more likely to pass on its genes to further generations. And so all this combined is a way of saying that genes that encourage traits that encourage survival are likely to disseminate through a population and become prevalent. And then we also have this idea of mutations, that the genes of an organism at any point can change to other values, and that allows for some flexibility in an evolutionary system. And so in that description, there were 4 key components, and I'd like to run through each one of them individually, because these will form the foundation for the 4 components of an evolutionary algorithm. So we start with the genes, and there's no agreed upon definition of what a gene is. I will be basing my definition on Richard Dawkins. And so he describes genes as being this smallest unit of selection. And this is a very flexible definition. It basically means anything that can last more than one generation, but also have some physical attribute corresponding to it. Something about the organism is described by that gene. And so an example of a gene might be your eye color, whether or not you have dimples. And then the possible values that a gene can take are called the alleles. So having dimples and not having dimples are the 2 alleles. And typically in biology, we consider alleles to have one of 2 states, but we're going to relax that completely to be a bit more flexible and let alleles take whatever values. They're basically whatever value a gene can have. And so if we had a gene for height, then the alleles would be all possible heights, so all positive real numbers. And so we'll be flexible on that because that will help us when we're defining these evolutionary algorithms. And finally, the key idea is that the genes and the alleles that those genes have will contribute to the physical attributes of an organism, and that will determine what the organism behaves like and how it's structured. So then we have this notion of fitness and selection. So every organism has an abstract value of fitness. We can't measure it directly, but this value will influence how likely it is for that organism to survive and in turn reproduce. And so genes that encourage fitness are more likely to create organisms that reproduce and so disseminate around the population. That is, strong genes will spread through the population. We then have this notion of crossover and reproduction. And so we'll focus only on sexual reproduction here, so 2 organisms, and they can reproduce together to have children. And each child will take half of their genetic material from each parent. But we can again relax that a bit more to make our evolutionary algorithms more flexible and say that reproduction generally involves a mixing of the genes. It doesn't have to be half and half, but just some way of combining those genes together. And finally, we have mutation. And that is that genes, or the alleles of those genes, can change at any time. And this is much more likely to happen at birth, but it can technically happen at any time. And so this idea is summarized in this diagram I've made. There's this implicit stage of development in which an organism is born and is raised in the protection of its parents. It will then go through this selection stage in which only the fittest individuals will be likely to survive. The surviving individuals can then reproduce and cross over their genes, and then that will produce children who will then mutate at childbirth to be slightly different from that natural combination. And all this is governed by the genes. That's the language of this process. And so how can we take this biological definition of evolution and apply it to the fields of data science or computer science? It turns out that we actually only need a few tweaks, that the translation is very natural. The first is that we replace these genes with the parameters of the model. So that is the various combinations of inputs to our model that we can change, and we're trying to optimize the output in response. We then replace this fitness with some sort of score measuring how well we're doing at optimizing. Maybe we're trying to maximize a value, in which case that can be our fitness directly. Or if we're trying to minimize a value, well, then we can negate that. So a positive value becomes good, and then that can act as our fitness. We also need to define how reproduction and mutation will work in the system. It's important to note here that there's no one correct formulation, that there will be many different ways to define the parameters, the score, and this reproduction and mutation mechanism. And the way you define it will affect how that evolutionary process develops. You might want a very aggressive optimization, or you might want a cautious one that makes sure it considers the whole space before honing in. And so choosing the formulation will impact that. So now let's look at an example of this in process. And so we will look at quadratic regression. That is taking a quadratic curve. In this case, it's minus x squared plus x plus 2. And this will be hidden from us. We're not aware of the actual values of this curve. Instead, we get noisy measurements that are these black dots here. And from that, we have to guess the 3 coefficients that would best fit this data. And by best, I mean minimizing least squares. That is, we'll fit a curve, we will take the distance of each point to that curve, and then we'll square that, average it over all points, and we'll try and minimize that total mean squared error. And we can do that using evolutionary algorithms. So we'll need to define those 4 key components, and once we have that, we can get started on letting evolution solve this problem. So we start with the genes. And in this case, we're going to use alleles, that is the values the genes can take, that are continuous. And we'll have genes for each of those 3 coefficients of the quadratic curve. And each of them will be allowed to vary between -3 and 3. And so this means that an individual organism will be defined by these 3 coefficients, and it will give us kind of the physical traits of this organism will be that quadratic curve governed by those 3 coordinates, or the 3 coefficients, sorry. And so when we first start our model, we will initialize all the organisms by randomly picking from this range -3 to 3 for each of those genes. We can then define the fitness and selection process for our evolutionary algorithm. We are trying to minimize this mean squared error, so mean squared, and that's the error here. And so we're going to have to negate that with this minus to make it so that maximizing it is a good thing, so that we can try and maximize fitness. And then with this fitness, we can define how we have this selection process. We'll start by ranking all the organisms by their fitness. We'll take a chunk off the top and let those ones survive. And then all the other ones will give them a small random chance of making it through. We'll then look at the shortfall of the population, and we'll let the surviving organisms reproduce to fill up that population. And admittedly, this isn't exactly how evolution works in real biology, but it doesn't matter. We've captured the general idea that only the fittest survive. And by letting the explicit fittest go through without any randomness, we make it more likely in this case that we'll get to a good solution, because we're guaranteeing that the best ones will get through at the start. And so really, it's all a matter of choice. I just decided on this method because it seemed appropriate for the problem. We then had this crossover, and so we take 2 parents, the mother and the father, and rather than splitting half and half, I decided to, for each gene, pick a random number between 0 and 1, and use that proportion of the mother's gene, and then the other proportion of the father's gene. And so it's some kind of arbitrary combination of the mother's and father's genes. And finally, mutation. For each gene, we have a random chance of that mutating. And if it does mutate, we pick a random allele from that gene pool, so any of the values in -3 to 3. And then we combine it in a similar fashion to in reproduction with the current gene. So we take the current gene, we have a certain proportion of that, and then the rest of it's made up of this random one. And we weight slightly this proportion in favor of the current gene. And that stops it from mutating too heavily and just running away. And so all those technical details aren't the most important. What matters is the results. And so here I've ran this optimization problem, and this is the results in an animation. So we start with the initial generation, and that is where all the parameters, all the coefficients are randomly chosen from that gene pool. And so as we can see, they're completely random. None of them really line up with the data. We can then step forward one generation. And so the worst organisms, the worst curves will be removed, and the other ones will reproduce, making the results slightly better. Now, they're not perfect yet, but they are starting to get there. We can go forwards once more, and we can see things are starting to converge. It's realized now that it's definitely this N-shaped quadratic rather than a U-shaped. There's still one there, but generally they're N-shaped. We put this forwards a bit more. We see it quite quickly converges on that true estimate. And with a few more time steps, I think we're about generation 6 or 7 here, it's pretty much solidly converged to the correct value. And then if we carry on, it stays there. We have some random mutations. That's the model trying out different things to see what will work. But because those aren't very good curves, they immediately die out and don't get to reproduce. And so we return to this quite strong group of curves here. And so I'll just play that in full so we can see what that looks like. Every frame is one generation. And one more thing we can look at is how the coefficients change with time. So the coefficients for x squared, x, and the constant term, I plotted them with generation. And for each generation, I've taken the average value of that coefficient over all of the organisms and added confidence intervals to show how close together those predictions are. And if we play this through, then we see that they're initially a bit off, and they start to converge to these black lines, which are the true values of the model. And so we see that they don't converge perfectly, they get close. Part of that is just because there is random noise in the model. We're getting noisy measurements, and so it's impossible to get the exact correct curve. But also that the evolutionary process we have isn't very aggressive. Because we're retaining those top few, we get to converge quite quickly, but then we struggle to really hone in at the end. And so if we wanted to be more aggressive, we could just change that fitness, that selection process to try and target what we're after. And so that clearly works, but there's no point in just saying how good it is by itself. We should compare it to the other methods available. So we'll first compare it to grid search. That would be trying out all possible combinations and seeing which work best. Let's imagine we're only considering integer combinations of coefficients. So -3, -2, all the way up to 2 and 3. And then we do that for all 3 genes. If we tried out all combinations of power of 3 combinations, that's 343, quite a lot. We might want to be even more precise and consider increments of 0.5, at which point we have over 2,000 combinations. Now, in this case, that's okay, because it's quite quick to train and evaluate our model. But if we were doing a more complicated system, well, this is going to quickly become intractable. And if we compare this to the evolutionary method, where we had 20 organisms per generation, and the number of organisms we had to generate was linear with the generations, and actually slightly less because some will survive through. And by about 5 or 6 generations, we were doing a pretty good job. Maybe every organism wasn't spot on, but if we averaged out over all of them in that generation, or the best ones at least, we'd get quite a good estimate of how well we're doing. And so really, we're needing far less than 100 to get the same sort of result. And more importantly, as we grow the search space, evolutionary algorithms will not get too complex as that space grows, whereas this grid search method will grow exponentially and will become intractable very quickly. We can also compare this to a gradient-based method. Now, this actually isn't the best example to talk about because, so I plotted here the surface we're optimizing over. So if we take the values of A and B that we possibly could have, I plotted how good the mean squared error is for each of those coefficients A and B. And we can see that actually this is a convex space. This is a nice valley-shaped surface. And so a gradient method a gradient-based method would work fine here. People may be wondering why I haven't included C here. Actually, if we include C, it just scales this up and down. The proof of that is there, or you can just take my word for it. And so, yeah, a gradient-based method would work fine for that, but there are cases where it wouldn't. And here's an example where, imagine we want to minimize this curve. So we have to choose the value of x that will give us the smallest y. If we were trying to do that, then we could easily, using a gradient-based method, get stuck in one of these local minima. If we started here, the gradient would take us down here, and we would be stuck there. We could overcome this by starting from multiple places and doing a gradient descent again and again. But if we're dealing with a very complicated model that takes a while to train, well, then this will quickly become computationally expensive, and we might not have the time to do it. And so an evolutionary algorithm would work a lot better in this scenario, because it could try all these minima in one go. And then once it figures out that this one's better, it could put its resources into optimizing around here. And really the key point comes down to how easy it is to calculate those gradients. In this case, because in the back I know the true equation of this curve, I can calculate the gradient, and it's quite quick to do gradient updates. But if we're having to approximate the gradient, or the gradient is hard to calculate, well then, when that's combined with these multiple starts to make sure we don't get stuck in a local minimum, that very quickly becomes computationally expensive and intractable. And in that case, an evolutionary algorithm would work much better. So I'd now like to look at a few examples of evolutionary algorithms in the wild. So these are examples of how evolutionary algorithms have been used that I haven't worked on, but give a more general sense of their power and what they can do. So here is an example I've taken of using the evolutionary algorithms to solve the traveling salesman problem. So for people who aren't familiar with this revolves around taking a set of nodes and trying to find the shortest path between them that connects them all up. And it's notoriously a very difficult problem. And yet, by defining this in a genetic sense, evolutionary algorithms can do a decent job of solving it, as you can see here. Another example here, by this YouTuber Seth Bling, is using evolutionary algorithms to play the game of Mario. And this was based on this paper, Evolving Neural Networks Through Augmenting Topologies. And it's worth mentioning here that even though this is involving evolution and neural networks, this is different to what I'm talking about today. This is all about evolving the connections within the neural network, where I'll be talking about evolving the whole neural network, its structure and parameters. But it's a similar idea and really shows how powerful these techniques can be. And finally, using evolutionary algorithms to make bipeds walk. So here's an example where at about 1,000 generations, they created an organism that could walk around pretty solidly. So really some clever stuff here. So we'll now move on to talking about neural networks, a very quick introduction to how they work and why we use them. And so this is almost a cliche at this point, but it's worth starting with that neural networks are loosely modeled on the architecture of the brain. That's why they're called neural networks. And the brain is structured with these neurons, which are connected together by these synapses. And when one neuron fires, the neurons it's connected to are likely to fire too if the signal being passed into them is strong enough. And then this can pass through the whole brain, creating very complex interactions between the neurons. And this allows us to capture complex interactions between the inputs to the system. So in our case, the things we see, touch, and smell. But in the case of an artificial neural network, the inputs we give it to the model. And so the idea is we take these inputs, we then pass them through these hidden layers. You can think of this as the brain of the neural network, and they're all connected with these lines, which show how signal is passing through the network. And then those will all be outputted to either a single value, a collection of values, really any sort of output. And looking at a bit more depth into how a neuron works, this is quite a complicated looking diagram, but really the idea is quite simple. An individual neuron will be connected to many inputs. So in this case, this neuron is connected to these 4 inputs, right? And each of those inputs will have a corresponding weight, which will tell the neuron how much it should take into account the value of that input. And when we're training a neural network, we try to optimize these weights so that they produce the correct output. And so we take these inputs, these x's, and for each corresponding weight, we multiply them together and then add them all up. And finally, we take this sum and pass it through an activation function. And this is typically some nonlinear function that just allows a neural network to capture some more complicated interactions than linear interactions. And then that becomes our output of that neuron. And so this is quite a small unit, but when combined together with many neurons, we can really capture some complicated behavior. There's also this notion of bias in a neuron. I won't get into that here, but anyone who's aware of that, I'm aware of it. And then the key idea is that we tune these weights, we train these weights by giving the model input data and the correct outputs to try and optimize these weights to give the correct output in the future. And so that's a very high-level summary of neural networks. And one thing I want to mention is that there's a lot of choices to be made when designing a neural network. We first have the structural ones. How many layers should we include in the neural network? How many neurons should we have in each of those layers? Which of those nonlinear activation functions should we use, if any? And what types of layers? There are the simple layers we saw in the last diagram, or the more complicated ones, such as dropout or normalization layers. And there's a lot of choices to be made just in that. We then add on all the choices of hyperparameters. These are values that govern how our neural network learns, how it receives inputs and responds to that. The first would be learning rate, how fast we should be learning. And we might want to be learning fast to get through our data quickly, but that also might mean we struggle to converge to the perfect solution. We have to consider the batch size, how many inputs to train on in one go. Smaller batch sizes tend to make our model generalize better, but will also take longer to train. We have to consider how we initialize those weights and the bias, what initial values to give them, and also what optimizer to use. That is the algorithm that governs how we update those weights as we receive new input data. So overall, there's a lot to do. If we tried to do a naive method of just searching over all combinations, we would be here for years. And so this is where evolutionary algorithms can give us a hand. So we'll look at an example now, and this is one that I created just to demonstrate how this would work. And again, a cliche is based on the MNIST dataset, which is a dataset of handwritten digits. And there are 60,000 of these which we use for training, for choosing the right weights and building that neural network, and then 10,000 which we use to evaluate how well the model is doing. And so the goal is to create a neural network that can accurately identify the digit seen in each of these images. Things a bit more interesting, we will make sure that the neural network only gets to see each inning. And this way we avoid having winning. If they're only seeing the images once, we'll have to balance out the model capacity, how much it can learn, and how quickly it can learn. It tends to be that very big models. So this makes a nice balance of those two behaviors. And so the space we're going to optimize over will be the number of layers, the number of neurons in each layer, whether we include this, how much dropout we use, or whether we use it at all, the activation functions we use, and the optimizer to decide the algorithm that decides what weights we're using. And so overall, this search space is about 10,000 combinations, which is far too much to be doing, even if you have a room full of GPUs. And so as before, we'll have to run through those four main components of the algorithm, and that will govern how this evolutionary process will develop. We start with the gene pool. This one is a bit more complicated than the previous one because we have more things we're trying to tune over. We have the number of neurons, the number of layers, all the way down to what optimizer we're using. And whereas before we optimized over continuous ranges, here we will optimize over a discrete space. So there are explicit values that these genes can take. The alleles are a set of values. And then once we have this gene pool, we can initialize a new organism. So when we're starting up this process, by just having a random choice of each allele for each gene. we then have to define the fitness of our algorithm. And we'll do this by training our model and then evaluating it on the test set and seeing what the accuracy of that model is. So good accuracy will mean good fitness, which is what we want. So the function for this is we simply fit the model and seeing the data one time and then evaluate how good the score is, how good the accuracy is. And then the process for selection is the same one that we had in the previous example. So we take the best organisms, keep the top few, let a few seep through, and then grow the population through reproduction to make it the same size as before. Crossover and mutation is slightly different. In this case, we will take the mother's value for a certain gene, the father's value for a certain gene, and then have a random choice between the two of them. So you either get your mother's gene or your father's gene. And that is the case for every gene making up that genome. And finally, mutation. We're going for quite an aggressive mutation here to make sure we can cover that whole space well. And so there's a random chance that each gene will mutate. And if it does mutate, we simply pick a random value from that gene pool corresponding to that gene. So completely random. And with that, we can let our evolutionary algorithm run and see what we get. And so, I'll play this animation here. This shows the generation and the average fitness, the average accuracy of all the organisms in that generation. So we see it sharply increases at the top, then it's increasing slowly. And then we have an interesting thing here where it drops down, but then it corrects itself after. And so I picked out this example because it highlights a real advantage of evolutionary algorithms. So for most seeds, for most random starts, this doesn't happen. It just improves to the end. I picked out this one to really hammer home this point. That evolutionary algorithms can make mistakes without that being the detriment of the process. So here, it was improving, and it made a few mutations, perhaps more than normal, by random chance, that made the average organism much worse. But because the organisms are spread out over a wide range of, they're spread out over the space we're optimizing over, the evolutionary process can figure out, well, these aren't very good, they won't survive, and then we get back to how we were before, in fact, a bit better. Whereas if we were using gradient descent, once we make a big mistake like this, we're likely stuck in one of these minima, and we won't be able to get back out. So this really showcases how evolutionary algorithms are quite robust to these complicated spaces with many minima. It can make a mistake, but learn from that and carry on to improve. And so the final result of this model was this combination of alleles, this combination of parameters. And so I obtained this by taking the last generation and aggregating over all the best organisms, so the top half of the organisms, and aggregating to figure out what they agreed upon. And it came out looking like this. So 512 neurons, which actually isn't that many, but a lot of layers. And so this is suggesting that you don't need many neurons per layer, but you need a lot of layers to capture the complexity of those images. That we shouldn't use bias, and that the dropout should be a fairly small number, but not zero. And finally, we have the activation and optimizer to be these things called ReLU and Adam. And these are what you would expect. These are very popular optimizers and activation functions. And so this is showing that, yes, it is giving us what we would expect. But this result here, that goes against my intuition. And so it was quite surprising to see that this evolutionary algorithm taught me something that I wouldn't have got by intuition alone. And so we can compare this to a random search. A grid search is out of the question. The space is too big. And a gradient-based method doesn't work because it's hard to define a gradient on these discrete variables. Like, what is the gradient between a ReLU activation and a TANH activation? There isn't a natural sense of gradient. And so I compare this to a random search. That is where we look at the whole space of models and we randomly choose them and see which is the best one. And so I ran this for some time, trying to see if any of them would be better than the best one in the last generation of the evolutionary algorithm. So of the 20 remaining at the end, could any of these be better than that best one? And I ran it up to about 500. At that point, my computer was getting quite warm, and I decided, you know what, let's just leave it there. And I think this could have gone on for quite a while without getting a better one, because it is just that, it's random. Whereas the evolutionary one is in the background, kind of, it's trying to optimize by using which ones work and which ones don't, and working more on the ones that do work. And so we'll now wrap up before moving on to any questions at the end. And so what are the next steps for this? So one thing I'd like to do would be to productionize the solution more, to try and make it more robust and have a more friendly interface. And then I'd like to experiment with different types of selection, reproduction, and mutation. So the moment I've tried a few of them out, they all work fairly well. I'd like to figure out which ones work best for exactly what I'm trying to do. There's also the possibility for training on multiple GPUs. Because in any generation there are multiple organisms, it's possible to train them at the same time to improve the speed of this process. And finally, I'd like to look at some more sophisticated initializations. My current approach has been to randomly choose initializations from the whole gene pool. But perhaps if I have an intuition of what alleles might work better, what values of those genes might be more performant, then I could maybe weight towards those so that they're more likely to be starting. That could make convergence happen a lot quicker, but still with the benefit that an evolutionary algorithm can explore and learn and might come out saying that my intuition was wrong and it would correct for that. So that's where this could go in the future. And so finally, some further reading. A good paper to look at if you're interested in evolutionary algorithms in general is this 2019 paper. It's on arXiv, which just kind of has a review of some modern applications and some techniques being used related to evolutionary algorithms. There is a book called Evolutionary Algorithms and Neural Networks. It is very pricey, but perhaps you can find a place to have a look at it just to see what a few of the ideas are. There are some very interesting topics discussed in there. And finally, thank you to Jennifer for pointing this out 2 code nights ago. There is this Twitter user called Hardmaru who has a website in which he publishes little projects on evolutionary algorithms and reinforcement learning more in general. And there's some really clever ideas there and some really beautiful simulations and animations showing how they work. So if you're interested in this sort of thing, definitely check that out. And so wrapping up, the source material can be found at this link, or it might be posted in the description too, not sure. And yeah, thank you everyone for listening. Thank you PyData for arranging this talk. I've had a lot of fun doing it, and I hope people have learned something of interest from it. And finally, I'll open up to any questions.
Thank you very much, Tim. That was fantastic. Yeah, you really helped break down the use of evolutionary algorithms really effectively there. I certainly myself come away knowing much more than I did before. So thank you very much.
Yeah, no problem.
I certainly should have added the GitHub link to the YouTube description, but we'll do it later on. So it'll be available. We'll also pop it out on Twitter so people can see it. So I guess first of all, what did you like? Was there a library you used to write the evolutionary algorithm code?
Yeah, so this was actually in base Python. So yeah, I struggled to find anything that did a really simple way of creating these algorithms. So all the neural networks were in TensorFlow, and I just built around that. Yeah, in base Python, because typically once you have those 4 main components, you define them, it all follows quite naturally. And so now that I've got that code, I can modify that quite slightly, and it all works the same. I believe there is a package for doing genetic algorithms. I found out about it a few days ago, which was a bit too late to change things over. But if you search for Python genetic algorithms, you might be able to find that package, but I think it's still early days.
Okay. Yeah, we can catch up after that one, after this, and pop it out on Twitter if we can find it. Yeah, so when you were discussing kind of how we can add different layers, optimizing the number of layers and the hyperparameters, is it possible to kind of figure out the optimal hyperparameters for each layer so that the hyperparameters can be different from each layer?
Yeah, so yeah, completely that would be a possibility. I try to keep things very small and simple here because it's just a prototype example, but you would be able to do that. And it's actually an advantage of where evolutionary algorithms come in. Because if you try to figure out the number of neurons for each layer and did a search on that space, well, that
Yeah.
space is massive now. It's also not got a fixed dimension. That's always going to be changing. Whereas it's possible using an evolutionary algorithm to have that massive space and still optimize over it. So with some tweaks, yeah, you can completely do that.
Yeah, I wasn't really sure how to approach that, but I think the way you describe it as a problem with changing dimensions, yeah, that's a really useful thing. I mean, I'm going to go away and Google that now because it's not
Yeah,
something I've kind of thought about before. I guess because obviously it's really difficult for an awful lot of algorithms to approach.
yeah,
Um, I noticed that you didn't have a comparison for like a Bayesian approach as opposed to.
yeah. So really, I think the Bayesian methods are pretty strong. The
Hmm.
problem is they're just very confusing and complicated. So even having a background in statistics, I try and read through the papers on exactly how they work, and I still don't feel completely confident in really that I know what I'm doing with them.
Hmm.
And so if you can really get a grasp of that material, then that is a good way to approach it. The one problem you might run into is when you're defining these priors. So when you're doing Bayesian statistics, you have to define your initial beliefs. In some cases, that can be simple to do, but in other times, it can be quite hard. And the problem is, if your initial beliefs are wrong, you put a lot of confidence in them, then it's going to be difficult for that algorithm to correct for that. And so, if you can get those right and you can understand it, then it's a great way to go. But yeah, it is complex.
Yeah, I mean, to be fair, when you're optimizing neural networks, I think complexity is perhaps to be expected.
Yeah, very, very true.
No, I mean it's the way you were talking about as well with the. I'm not sure what the technical term is, but when you're selecting your next allele,
Yeah, yeah,
you mentioned you've kept it simple and used a random chance.
yeah,
Usually, you can, as part of your changing dimensions, you can incorporate a distribution and change the parameters of that distribution over time. I imagine that's probably incredibly complex and only for real niche cases, but it sounds like this approach could be combined with a Bayesian approach or elements of Bayes
yeah,
theory.
yeah, definitely. I mean, yes, you can definitely easily incorporate those initial beliefs, but then you're perhaps not tied in as heavily as you would be with a Bayesian method.
Mm.
But yeah, I mean, that's the thing. Like, as long as you have those four components, you can make them as complicated as you want to, and the same idea will still work. The key thing is allowing your model to try multiple different things in one go and see what works. That's the key idea behind this.
Yeah, yeah. I mean, it's really fantastic. I mean, looking at it compared to, I mean, I've played around with Bayesian optimization before, and obviously relative to grid searches, it's very, very powerful. But even then, it can still. I mean, I'm not. What kind of generation time are you looking at? Because from Bayesian approach, you can still end up with quite high computational costs. It seems like for this, you kept it very, very low cost indeed.
Yeah. So another thing, yeah, if you want a very rough solution, after a few generations, it'll get a pretty good job, and then it takes a bit more time to really narrow down those solutions. But yeah, compared to the gradient-based methods or the random searches, it completely yeah, it's completely better.
Yeah, no, it's fantastic. Okay, I think we see if we got any questions in the Slido. So you've mentioned some of the shortcomings of gradient descent, which seem perfectly reasonable. What are the shortcomings of evolutionary algorithms?
Okay, so I guess part of it is that there is a lot of scope for subjectivity, that you do have to define how you want those processes to be defined. And so if you define them a bit poorly, so I can remember when I was creating the solution, I accidentally got it so that the chance of mutation was inverted. So rather than being a small number, it was really high. And I
Yeah,
was you're building these models, and it was just getting complete garbage out. And so if you don't have those set up exactly correct, I mean, that's still valid. You know, you could have mutation every 90% of cases. It's just not going to work very well. So if you don't get those nailed down, then they will fail. But I think there's also a lot of flexibility in that, more so than with some other methods. You can get it a bit off and they'll still perform pretty well.
yeah.
And
I
then I
mean,
guess,
sorry.
go on.
No, no,
Yeah.
please.
So I think, yeah, so another issue might be that there still is a fair amount of computation involved. I guess, yeah, that's perhaps it, that evolutionary algorithms really come into their prime when you're optimizing over very big spaces, because you have to have those multiple organisms. If you're optimizing over maybe a two-dimensional space, it's not really worth it. There's almost a startup cost of having all those organisms. But once you're dealing with a really massive space where all other algorithms are growing like exponentially, or perhaps some high polynomial, the evolutionary one grows a lot slower, and so it really becomes more advantageous for those larger cases.
It seems like it would also be quite easy to parallelize.
Yeah, I mean, completely. So if you had, this case is getting enough GPUs for the number of organisms is tough. But if it was something on your CPU, say, and you had an 8-core CPU, you could run kind of half a generation at a time and get through that very quickly.
Yeah, no, that makes sense. Cool. So have you got any theories on why genetic algorithms aren't more widely used in this kind of use case?
Yeah, it's interesting. So, so when I was researching initially for this project, I had a look into what are the common approaches, and the main one is this package called Hyperus, which is kind of a port of hyperopt for hyperoptimization in Python for Keras. And I was looking at that, and it looked quite promising. But then I got to the end, I realized, oh, this is just doing random search, and it was really slow. I think the problem is that a lot of the articles promoting these methods always use these toy examples. And for a toy example, it's very easy to show, look, random search, it works great. But when you scale it up to these more complicated models, well, then they don't work the same. And so I think because people on Medium tend to share these simple ones, it's more easier to use those.
Yeah.
I think another part of it is that, they are a bit more complicated. You do have to have that set up. Now that I have that code for evolutionary algorithms, I'd be quite happy to adapt that in 15, 20 minutes for a new model. But getting there in the first place was a bit more work. And now that I'm aware of this Python package for genetic algorithms, I'll have to see how good that actually is. I only recently came across it, but perhaps that makes the process even simpler. In the future, these will become more popular.
That's a good answer. It's certainly we've certainly seen that with a lot of other technologies as the libraries make it easier to become more prevalent and then go from low level to high level and easier to use. They certainly get an awful lot more use, like, for example, Keras, as you mentioned.
Yeah.
So you mentioned a couple of references. Would you say any of those are very useful to someone who's a beginner to search hyperparameter optimization?
Yeah, so if you want quite a high level overview, just more kind of what this can do and the range of problems it can solve, then that third link to I forget what his name was, but yes, some of his work is absolutely brilliant, and so that's a really good way of getting introduced to those ideas. I guess for a more light view, if you probably just Google evolutionary algorithms on Medium, then you probably get quite a good introductory talk about it there. I didn't want to link any of them because they're all about the same. I have no favorite there, but there is plenty on evolutionary algorithms. Applied to neural networks, a bit less so. But yeah, if you want to get a general grasp of evolutionary algorithms and what they can do, then yeah, just having a search or that third link is probably the best place to start.
Cool. I would say your GitHub also looks very promising as well.
Thank you.
So I think that's all the questions we've got. Feel free if you've got any more questions, then feel free to message us on Twitter, and we'll try and put them in front of Tim, or someone else in the community can certainly get involved. But Tim, thank you very much for joining us. Thank you to everyone for your questions, and we hope to see you next time.